Hello, Sai, sir.
Yeah, good morning, sir.
Very good morning, sir. Sir, shall we wait for 5 minutes to start, sir?
Yes, sir. Okay, sir.
Sir, good morning, Srinivas, sir.
Yeah, good morning, sir.
Sir, we will start the session. The participants are already.
So, sufficient number of participants have logged in, sir?
Online, there are only 12, but here offline, there are 30 people, sir.
Oh, okay, fine.
Okay, so it's fine, sir, no issue. Huh?
Okay, I'll begin, sir.
We'll start.
Very good morning to all the participants. I welcome
Yes,
you
sir.
all for the Day 3 FTP program. We shall continue from the one which we have left yesterday. I hope everyone got familiarized with how to design a sequential logic circuit designs. So yesterday we have designed a simple counter example. Now I request all the participants to just open your design source files. I mean your project file of the counter based design that we have done. There is a small extension of some important concept is there that is still pending that I will be covering it today. So let me share my screen first. I hope my screen is visible to you all. Sir, please confirm.
Sir, Chapani? Sir, tell me, sir, Srinivas, sir.
Sir, screen is visible now, sir.
Your screen is visible, but still, actually, there are some technical glitch here. All the displays are not connected, but the students, I asked them also to log in. We will continue, sir, slowly like this till it is resolved. You can continue.
Okay, I will continue, sir. At the earliest, try to resolve the technical issue. Yeah.
Sure, sir. Sure, sir.
So yesterday we have we have written the test bench and we have just simulated with different conditions and we have checked the functionality of a module. So I want to present today some little bit advanced concept in the test bench. So for that, let me open MS Word file. Yeah. So, as per industry standards, maybe we might be having some algorithm or maybe a process. Uh, so for which we are going to design a circuit. So mostly the circuit means a digital circuit. So whenever we are having any algorithm or a process, so what we will do is we will try to model it in any scientific programming language. So what are the popularly used scientific programming languages? Say for example, C, MATLAB, Python, so on and so forth. So whenever you are having any algorithm or a process, when you are modeling it in any scientific programming language in this fashion, you will be dealing with data. So you have an algorithm or a process, you will be giving some data to that process, and you will be getting some this data, we call it as data in. And once that algorithm is processing this input data, and at the same time it will also generate some output data. So that for your reference I'm calling as data out. So what is the magnitude and order of the data? So this data can be pretty large. So nowadays the term called big data is very popular. So we have tons of data. And for this, in order to do this processing, we are taking this algorithm into the hardware level, and where we are designing a specialized custom hardware circuit for to process this algorithm. So earlier you have implemented that algorithm in scientific programming language, and that program is being run on your general purpose processor, and you are giving data, it is running and it is giving you the output. So the performance just varies because the general purpose processor is designed to handle multiple tasks at the same time. So that is a different aspect. We don't talk about the performance. So in order to get a very high performance, we will be designing a dedicated hardware architecture. So only thing is we will map that algorithm into hardware. So once we got a hardware for that algorithm, again, as you have seen, once we have designed the circuit, what we have done the simulation to check its functionality. So checking its functionality is nothing but for a simple test benches, what we have written, we have just checked its functionality by using few test cases. But in real-time scenario, those few test cases is not sufficient. Just in the case of a software, how you have given a large amount of data to run that algorithm or a process, and you have generated some data out. So this is an order of a very high magnitude, maybe tons of data. So even in the coming to the hardware point of view, it is also mandatory to give that much tons of data in the simulation environment and check the data in the check the data that is generated by your hardware module. And you need every time you cannot scroll the timing diagram and check each and every data sample whether data is coming or not. In our counter based example, we have seen we have designed a 6-bit counter, so it is generating the count values ranging from 0 to 63. So if I design a 16-bit or 32-bit or a 64-bit counter, then the count values will increase exponentially. So it is not always possible to scan through the timing diagram and check each and every value. So instead, what we will do is, as per industry standard, we will write test benches in such a way that when we run the simulation, we will be getting a timing waveform. That is okay. That simulation we will run for some predefined time, say for t nanoseconds. And accordingly, the timing waveforms, you can see outputs or whatever the outputs we are coming, it is being represented in timing waveform. If you want, you can just scroll and check the data randomly. But since we are dealing with a huge amount of data, it is very difficult to check each and every sample, right? So for that purpose, what we do is within the test bench, we will write few statements or a code that is associated to handle the data. So how to handle the data? Maybe you want to check a few outputs, whether how the hardware is generating. So those output lines, what you do is you will write some conditions. Depending on that condition, you would try to log that data output into a text file, .txt file. So from the simulation environment itself, you are capturing the data that is generated by your hardware module, and that data you are trying to store it in a .txt file. Once after the simulation is over, if you close it, you will end up in generating a text file, where in the text file you will have the outputs generated by your module. What type of outputs? Maybe the module can generate n number of outputs, and you want to check all the n number of outputs, you can log all the data into the different text files. Or else if you want to check one by one, you can log all the data one after the other in a text file, and you can save the data. Once this data is saved, what we will do is we will import this data again in a scientific programming language, what we call it, maybe a C, MATLAB or a Python of your choice. So whatever the data that we are getting, this we call it as maybe test data. Actually, in your scientific programming language, you have run already that process, and from that process you got the expected output. That expected output data, that we call it as golden reference. So that is our reference data. So we call it as a golden reference. And the data that your hardware module has generated, that you have logged into a text file, that data we call it as there is no specific name. You can call it as simulated output data or something. So what you have to do is the data which your hardware has generated, that you have to compare with the golden reference data. That is the actual data that you have obtained by processing that algorithm or a process in a scientific programming language using the input data. So the golden reference data, the obtained data, hardware data, is compared with the golden reference data, and it should be equal. Then only you can say like whatever the functionality you have mapped into the hardware, even the algorithm is performing in the same way as in the software. The algorithm is performing the circuit what you have designed for an algorithm, that is working fine, similar to the one that is actually being tested in software. So in this way, we will compare the actual data and the obtained data. So for this purpose, we have to use some file handling IO operations within the test bench. My motivation for in this example is, I will just show you how to log the output data into a text file. Similarly, in order to do the simulation, instead of giving the test cases manually in the test bench, you can also import the data from a text file, and you can read the data serially from a text file, and you can give it to the module, check the output, and that output you can put it into the another text file. So input to a module, you can also take it from a text file. Output, you can dump it into a text file. So how to take the input and test a module using a text file, that will cover in the later part of any example. Why? Because in the counter based design, we are not at all giving any data input, only we are giving a control signal enable, and that counter is running freely, and each and every clock cycle it is generating the count output value. So here we are only getting the output data, but we are not giving any input data. So for that purpose, in this scenario, we will check one scenario where we can log this output data into a text file. So that file IO operation to log the output data, that we'll cover in this example. In the later part of the examples that we'll do in this FTP, at that time I will show you how to give data input to the module for testing directly from a text file, instead of giving the data within the test bench file. So I think I am clear with this aspect. So let me quickly go to the Vivado software. I hope all the participants have opened the yesterday's project where we have done the my counter 6-bit design. So if you remember, we have written a test bench, right? My counter 6-bit underscore TB. So we will write a second test bench. So don't disturb this test bench. You can keep this as for your reference. So we will write another test bench where we will check the file IO operations. So what you can do is you can go to add sources, click on create simulation sources, and click on next and create a file. Yesterday you might be given some generic name, right? Some name underscore TB. Now you can use similarly the name underscore TB, and this time after TB you give some numeric value 2, that is test bench 2 for your understanding, and then save it. And just you open that file. Once you have created, you will be anyhow getting the blank file. So what you can do is you can just copy the code of our previous test bench, because we can reuse that code because majority part of the code remains the same. So you can just copy it and you can just paste it in your new test bench file. So I have just for your understanding, I'm showing you the steps. So I have copied and pasted it in new file. And when you're copying and pasting it, again, the module name will change. So make sure to give the new module name, I mean the test bench file name. So here I give my counter 6-bit underscore TB2. So I think I'm clear till this step. I will just wait for 1 minute. If your participants are still lagging behind, you complete this step till this process. Mahesh sir, is the technical issue has been solved?
Yes, sir, it's resolved.
Okay, now they are able to see on the screen, right?
Yes, sir. Yes.
Okay, Professor. So now we have created a new test bench module. So my counter is 6-bit underscore TB2. So the inputs remains the same, outputs remains the same, instantiation remains the same, initial conditions remains the same, clock signal remains the same. In the test stimuli, yesterday we checked for different conditions, right? But these many things are not required. So the first one, reset, is required. Next reset we need to release. Next, enable is required. After that, enable should be released. And these 4 statements are required, and the bottom 4 statements are not required, so we will delete it. And you can see one thing, after resetting you are making the enable to be high, and since this is a 6-bit counter, maximum it will count up to 64 states, so 0 to 63. So 64 states in 64 clock cycles. Here the clock cycle duration is 10 nanoseconds. So the counter will reach the maximum count value after 64 clock cycles. So that 64 clock cycles into each clock cycle is having 10 nanoseconds delay. So total 640 nanoseconds. So I just want to run the simulation for 640 nanoseconds. After 640 nanoseconds, what I'm doing is I'm making the enable to be 0. So this is the test stimuli. What I'm doing is, now as I told you, in this test bench, my main motivation and interest is I want to capture the output, that is count, the count output that the module my counter 6-bit is going to generate. That count values I want to store it in a text file. So for that, what I have to do is, first I need to create one test bench variable. So maybe after the inputs and outputs, I'm just making a comment. So test bench. So in the test bench variables, I want to create a variable called as a file pointer. So the data type is integer, integer file pointer. Any generic name, I gave it as file pointer. You can give it any other name of your interest. So why this file pointer is required is just like it will be pointing to a file. So with this file pointer itself, we will be discussing it further, and we will be telling to the Vivado that we will be addressing that file with respect to a file pointer. Its main purpose is to point to a desired file. So maybe after instantiation, after initial conditions, what you can do, maybe after clock signal, you can just open the file. So open file. So for that, again, all these file operations should be placed inside a procedural block. So inside a procedural block, so the procedural block I am using is initial, because I don't want this file to be opened continuously all the time. I want it to be open only once. That's why I'm using an initial block. So after that, it should have begin and it should have end. So this is a syntax. So in this, what I am doing is initial begin and I have to open the file. So in order to open the file, the Verilog keyword is $fopen, and here you have to give in the double quotes the file name with and in another second double comma, in second double quotes you have to write what is the mode it has to open. It has to open the file in write mode, so that's why I keep it as W. And what is the file name? Say for example, I give the file name as data out.txt. So you can give like this, and if you give like this, so in which path the file will actually save. So to the best of my knowledge, if you open your Vivado folder, project folder. So my project folder name is lab2. Under lab2 you can see Vivada has generated so many folders, right? So there is a folder called lab-2.sim. Under this there is a sim_1 folder. Under this there is a behavior folder. Under this behavior folder there is xsim folder. The file will be created by default in this location, and the lifetime of this file will be dynamic in nature. It is not fixed, so whenever you relaunch the simulation the old file will delete. So if you want to preserve better, what you can do is you can go to lab-2.srcs, that is sources. In that sources there is sim_1, that is simulation sources. In that there is a new folder. You can copy this path because in this sources folder the files will not delete. It only thing is it will be overwritten if you relaunch the simulation. But in case of other folder, the default folder, even if you're doing even if you're not doing this simulation, if you're doing any other simulation also within this project folder, it will flush all the files. So it will delete all the files and it will regenerate new files. Say for example, within the module you will be doing some n number of test benches and n number of simulations. So whenever you are redoing any other or running separate test benches, the common directory, what it will do, it will remove all the files of a previous simulation carried out by a previous test bench. So as of now you can see in our design we have two test benches as of now. So we don't want our file to be deleted when you are simulating other test bench. So for that purpose, I want to change the path. So you can use the path over here before the actual text file. And make sure, I think this should be / if it is in Windows. If it is in Linux, it should be as a / so that you can change it. So appropriately you check your actual path. You check and you just give the actual path. So in this case my path is C user secure desktop FTP day 1 lab2.sources sim1 new. Inside the new folder it is data out.txt, and in that folder itself I am also having the test bench files as well. So I have given that a common path. So once you have given this, what you have to do in the test stimuli, you are resetting your module, releasing the reset, and you are enabling the module, and after a delay of 640 nanoseconds you are disabling the counter. So after that what you can do is have to close the file. So once you have opened the file, at the same time you should be also properly close the file, otherwise the data log will not save properly. So which file you are closing? The file that is pointed by the file pointer, that you have to close. And after that, if you want the simulation to stop, you can give $stop. So now we have opened the file, we have closed the file, but we have not written any command to write the file. So that writing file you will be writing as a separate code at the bottom. So write data text. So how do we write the file? So we write a again, this is a procedural statement, so we are using always. So we don't know, this writing should not be like an initial process. It should be as a continuous process. That's why we are writing always statement, because when we don't know when the data will become active or when the data is inactive. So we have, whenever the data becomes active, then that copy of the data coming on the output line should be written into a text file. So for that purpose we have to write always. You can write sensitivity list as required. So my module is generating data on every positive edge of the clock, so that's why always said postage of clock. And you can define the input conditions, when to log the data. Generally, as per industry standard, what we do is, I will just check it. For every data out value, uh, for a high-end designs, what we talk about. So if this is a module and this is generating some data output, for equivalent to that output, we will have a data out valid. So for every data output, we will be having a flag output, that we call it as data out valid. So when we know that the data on this data out, whether it is a junk or a garbage value or a valid data value, when we know means whenever the data with reference to data out valid only, we will speak that whether the data on the data out bus, actually this is a bus, data out valid is a single bit. Whenever data out valid is high, then only we assume that the whatever the data coming out of this data out bus is a valid. So if we don't have this data out valid, we don't know whether the data on this data out valid is a valid output or a junk or a garbage output. So this is the scenario. For every data that we are going to, wherever the module is going to output, we will be using a status signal called as data out valid. This is as per the design procedure, general design procedure. So whenever you are designing a module, there are certain design rules. Why? Because this is not the ultimate. Because our module, we have designed one module that is not the ultimate. It is generating data. This data should go to other module for further processing. So how do you intimate to the further subsequent module that this module is giving the right data? So for that only we will use some status signal. Whenever this data data out valid signal comes, then the subsequent module, maybe M2, will understand that M1 is giving the actual data. Then M2, what it will do, it will try to read the data and it will do further processing. So this is somewhat like handshaking. So in order to have a perfect handshaking, you, apart from the control data signals, you also has to establish or design some handshaking signals for the smooth transfer of data from one module to another module. So there are some standard protocols are also available. You can follow those protocols, or else you can redefine your own protocols. Maybe you can use some signals like ready to indicate the status of the module, whether it is idle or whether it is busy. Next, done tick. This indicates that the module has performed the task completely, and data valid, like this. There is no particular rule like you have to use only these set of signals in this fashion or log. You can define your own type of handshaking signals so that this module will be acknowledged in the subsequent module, and there will be a smooth transfer of data from one module to another module without missing any data samples. So but in our case, we don't have a data out valid, so we don't know when the count value is coming. But not an issue. We can use the input condition. So whenever enable is high, then we know that the counter is counting. Whenever enable is 0, the counter is not counting. So when the counter is not counting, we are not interested in copying the data into the text file. Why? Because the data remains a constant. So in that case, what we can do is we can use that condition as that condition can be used so that we can log the data. So for that purpose, what I'm doing is if enable. So whenever enable is logic 1, what I am doing is I have to write the data into the text file. For writing the data into the text file, we use a command called $fwrite. You give the file pointer. So in which file we need to write. So that file pointed by the file pointer, and how we need to write the data. So for time being, I'm putting %d. That means in the decimal format, it is going to write the data. After writing the data, it should go to the next line, new line. So this is similar to C. And which output data it needs to write into the file. So that output is our output wire name is count and semicolon. So now you can just save it. So these are the conditions. So only modifications that we have done in our test bench is we have written command to open the file, a new file in write mode, and then we have written a command to close the file at the end of the simulation. And during that simulation, whenever a particular condition occurs, then we are asking to copy the value of that particular output in the file in the specified format. This is important. Here we are storing the data in decimal format. Now you can save it. Once you have saved it, what you can do, you just this is a file, right? You have written file pointer under the code for file IO operations. So what you can do is in the sources tab under the simulation folder, you have to select your new test bench file, that is tb2, right click on it and click on set as top, because this time you want to simulate your architecture with the new test bench. So I think earlier the top module of your test bench is my counter 6-bit underscore tb. So now you have to change the top module, that is my counter 6-bit underscore tb2. Once this is set as a top, you can click on run simulation and click on run behavioral simulation. So it will launch you the simulation. And if you remember, once you launched a simulation, earlier we have run our previous test bench. That test bench timing waveform, I think you might have saved. Whenever you launch the test bench, it will open the previously saved file having an extension WCFG. So earlier you saved the test bench file, right, with the timing waveform diagram. Now you have changed it to test bench and you have relaunched it. So what it will do is it will open the previous file. In that file, no waveforms will be available. It will be a blank file. But don't try to run the simulation in this file. Why? Because if you have saved any settings, that will be erased. and it will be edited. Because once again, if you go back to your previous test bench file, if you set that as top and if you relaunch the simulation, with respect to your previous saved settings, you will get the timing waveforms automatically. So I don't want to disturb that file, so you can click on close. Instead, what you can do is click on file, go to simulation waveform, and you click on new configuration. When you click on new configuration, you will get a blank simulation window. Now this time you save that window. When you save that window, it will save that waveform file, that is wcfg file. It will save the simulation file with an extension wcfg. So a new file will be generated for this second test bench. Once this new file is generated, now the simulation window is completely blank, right? So on the left hand side, you can see scope. In this scope, you select your test bench. Under the test bench, you have DUT. If you want to observe DUT signals, you can select DUT and you can add it. But I want to observe only my test bench signals, that is input output. Anyhow, my DUT output is connected to the test bench output. So you select this test bench, and when you select the test bench, here under the object section, it will show you the list of wires or signals which are available. You select all the signals, click on right click and click on add to waveform. So all signals will be added to the waveform. And after that, you can click on relaunch. So it will relaunch the simulation. So once it is relaunched, since you have used $stop, after performing the simulation, it will stop automatically and it will take you to the test bench file and it will highlight the command where you have written $stop, indicating that it has stopped the simulation. Earlier, you can see simulation by default runs for 1000 nanoseconds, but here at this time it run for only 670 and it got stopped automatically because we use it the $stop. And now you can click on zoom fit and you can change the radix of the count to unsigned decimal. You can just scroll and check. After see the count value after the 63 count, you got the 0 to count value and the simulation was stopped. And at that time enable also was made to be 0, that you are not able to see why, because it has stopped. So we will run for yeah, now you can see here the enable is made 0 and the counter has stopped it after 63 third count. It has stopped and it has retained the value 0. So this is simulation. Now what you can do is you go to this path, whatever you have given the path, right, where your actual text file is saved, that is data out_txt. You go to this path and you will see a file is created with the given extension and a given file name. So this is the file. So if you double click on the file and just open and see all the data output, the output of the count wire. The counter output has a wire called count. So this count, on this count only you are getting the count value of the registers, count value of the counter that is driven via the count register. So all those values are being saved in your text file. So you can just scroll and see count values from 0 to 63 are successfully stored, and the data is stored in decimal format. Now what you can do is you open the simulation in the test bench file, go to the command where you are writing your data to your text file. Here you have given the format specifier as %d, that is decimal. Now you change the format from %d to %b and then relaunch the simulation. This time it should save the data in binary format. So once the simulation is done, again go and open the file. Now you can see the data is stored in binary format. Similarly, you can change it into H, that is hexadecimal, and again if you relaunch the simulation and then open the file, you can see the data is stored in hexadecimal. Just open the file and you can see this is a hexadecimal representation. Similarly, I think you can also give O, you will get it in octal. Relaunch the simulation. Just open the file. This is an octal representation. So I think this is very much clear. So once you get it as a data file, this you can import into your scientific programming language and compare with the expected output, and the outputs generated by the hardware module when it perfectly matches with the expected output given by the scientific programming language. At that case, we can confirm that whatever the hardware which we have designed is functioning with respect to the desired functionality. So this is one of the important file handling operations in test bench. Similarly, there is a provision to load data from the text file and do the simulation that we will cover it in another example. So I hope this is clear. And I think the participants are also done along with me. If you people are still doing it, I just give you some 5 minutes break. You can just complete this experiment. Then we will move on with the next experiment. In the meantime, if any participants has any queries, you can just interact with me and ask. Or if they have any problems facing, you can just share your screen so that we can address your issues. That's it from my side. Mahesh sir, please take control. We will take just 5 minutes break.
Sure, sir. Hello, sir.
Yes, sir.
One of the student has it out.
Okay, sir. Yeah, let me know, sir.
Sir, good morning, sir.
Yes, madam, tell me.
Sir, in our code, you uploaded one file in open file. Hello.
Yes, madam. Tell me.
Sir, the open file, you upload one file. So, no, sir, that is not clear.
Okay.
In open file, initially, fopen data out text, sir.
Yes. I'm just sharing my screen. Just a minute. Yeah.
Yes, sir.
You can see a doubt over here. So we want to save the data into a text file. So for my reference, I named the text file as dataout.txt. It can be any text file. So first of all, what you have to do is Vivado should open that file. Opening in the sense, if a file already exists, it will open. If file is not existing at that directory, what it will do, it will create a new file with that name and it will open that file in write mode. It is just like a C. In C, you have file IO operations, right? So opening a file in read mode, write mode, append mode. So in write mode, if you are opening an existing file, what it will do, it will remove all the entries which are previously stored in that file and it will write the file freshly. If you open a existing file in append mode, what it will do, whatever previously data that has written in that file, it will leave it as it is and it will go to the next line and it will continuously write the data. So in this example, what I'm telling is we want to store the data in a text file, output data in a text file. So for that, what I'm doing is there is a command in Vivado, there is a command in Verilog. So that is called $fopen, and it has a syntax called, first you have to give the file name followed by the mode of operation. So the mode of operation is write mode. And what is the file name? That is dataout.txt. You can use simply dataout.txt. Then what it will do, by default, it will create that file in this location. Which location? Maybe in your topmost directory of your project. If you go, you will have sim folder. In sim folder, you will have sim1. In sim1, you have behavioral. In behavioral, you have xsim. In this directory, it will save the file. But in this directory, whatever the files you are seeing, all these files will delete automatically whenever you are launching a new simulation. So I don't want my file to get deleted if I launch any other simulation within the same project environment. So for that, what I'm doing is I am giving my own specific desired directory. So like that, you can give any other desired directory as you wish, where you want to save the file. That that directory will have a path, right? So if you click on top here, this is the path. C user Satya desktop FDP, so on and so forth. This is a directory, and this directory has some path. So that path you have to give here in the fopen. You define the path. Along with that, at the end, you have to define your file name. Or else, if you are comfortable, then you can give the file name as it is, and then a file will be created and it will be open from the default directory. So that's it. I think I have addressed your query. Do you have still any doubt in this file opening operation?
No, sir.
It is clear, right?
Yes, sir.
Okay. Yeah, welcome back once again. We will continue with the further experiments. But before that, let me present my screen. Okay. Yeah, fine. Yeah, so far we have seen one combinational logic circuit and a sequential logic circuit. If you remember, we have done the implementation of a combinational logic circuit on FPGA. So if you notice that at that time what we have done is we have a black box, that is our logic, combinational logic. Maybe we have designed the gates, right? So it has inputs and it has an output. So what we have done is these inputs we have configured to the dip switches of FPGA development board, and this we have outputs we have configured connected to the LEDs. So these inputs and outputs we call it as GPIOs, general purpose inputs and outputs that are available on the FPGA development board. So since the we have seen the basis tree of FPGA. In that we have 16 dip switches, dual inline package, slide switches, and we have 16 LEDs. So if you take any other configuration or any other development board, the count more or less won't be the same. If you take very high-end board, say for example Z board, I think you have 4 slide switches and 4 LEDs. So it is not always feasible for you to connect your hardware module inputs and outputs to the GPIOs which are available on board. Say for example, if you are dealing with 32-bit data input or a 64-bit data input, so you cannot find any FPGA development board with 64 bits, 64 number of DAP switches or 32 number of DAP switches. And also giving inputs via the switches is also a very tedious task. Maybe for an adder or a gate, for to check its functionality, we have just connected to switches and we have done. But if you take into consideration about the real-time or a complex VLSI digital systems, where we'll be having a module with a pretty large number of inputs and pretty large number of outputs. So it is not always possible to give all these inputs to any slide switches or anything, and it is also very difficult to operate. So these inputs and outputs we cannot always connect to the GPIOs. So in that case, how do you in order to test your hardware circuit, whether it is working as per the desired functionality or not? So how do you do that? Testing in the sense real-time testing. I'm talking about real-time testing, not the simulation. In simulation environment, anyhow, you will from the timing waveform diagrams or from the file IO operations, what I have done, you will be able to log the data and you will be compared with your reference data and you can check the functionality. But it is not always the same. If the simulation is valid, it doesn't mean that the real circuit or the circuit which is sitting on the real FPGA chip, it will work in real time. There is no guarantee. Even if the simulation is passed, there are few scenarios where the chip used to fail at the implementation level or else after the bitstream generation. And even if you implement on FPGA, there are few scenarios where due to unforeseen circumstances, the circuit is not performing as per the desired functionality. Maybe it is generating a garbage output, even though the simulation is valid. So you should not always rely on a simulation. You have to check the simulation, that is only for a preliminary checking in order to proceed further. So once a bitstream is generated and you are implementing your actual hardware circuit or realizing your hardware circuit on an FPGA, even on the FPGA also you need to just check the performance in real time and assess that your hardware circuit is fully functional as per the desired requirements. So that we call it as real-time testing, RTT. So if your module is having a pretty large number of inputs and outputs, then how you give those inputs to your FPGA and how you do capture those outputs and visualize and check whether your circuit which is actually sitting on FPGA is working as per the desired functionality or not. So for that we have a concept called debug course in Xilinx Vivado. We also call it as debug probes, or we can also call debug course, or other name is IP course. IP stands for intellectual property. So now what we do is we try to use these debug cores or the IP cores, what I'm talking about. So we have our module, right? To this module, we will interface one or more number of IP cores towards input side and other IP cores to the output side. Via these IPs, we try to provide inputs to our module, and the outputs of our module we try to capture connected to the IP. Through this IP, we try to visualize the functionality. Visualizing this functionality means not at the simulation level, at the chip level. So when your actual circuit is sitting on FPGA, we are visualizing its performance in real time. In this case, we can try to avoid the use of dependency of dip switches and LEDs. Even by using the IPs, you can reduce the number of inputs and outputs. Even some outputs you can still connect to LEDs if you desire. And some inputs again you can give via the dip switches. But majority of the inputs and outputs that you cannot give via the GPIOs, that you will give by using IPs. So that is the main concept over here. It's not like when you're using IP, you should not use switches and LEDs. You are still free to use them. But it depends on what you desire. So this is the main concept that we are going to deal with. So again, for this purpose, we will be using the same counter, my counter 6-bit design and we try to implement this design along with the IPs on FPGA. So let's begin. So how do we proceed is like on the left hand side under the flow navigator, you can see under the IP integrator there is an option called create block design. So you please click on create block design. And once you click on that, it is a dialog box appears for creating a block design. And it is asking you what is the design name for your block design. I'm just leaving it to by default, that is design_1. And without disturbing other options, you can click on OK. So now the Vivaldi environment is creating a new block design. And the block design environment is newly created. So in this, what I'm trying to do is, now on the left hand side you can see design. Adjacent to design there is a sources, that is our previous dialog box. In that sources you can see under the design sources one design, a block design, that is with an extension called .bd has been created. And beneath that we have our Verilog HDL description of our counter, that is 6-bit counter. The module name is my counter 6-bit. So what you do is you need to add this Verilog description of our counter in the form of a block design in this block design environment, that is at the right hand side. So how do you add it in the form of a block? So first right click on it and click on add module to block design. But before doing that, just please open the term my counter 6-bit.v. You need to do small editing over here. In the my counter 6-bit, if you see under the sequential logic, we have given the reset condition to be active high rate. if you are getting reset to be logic 1 or logic high, then the counter register is getting reset to 0. Instead of active high logic, I recommend you people to use active low logic. I will tell you why. You just keep a tilde symbol just before the variable name, that is reset, and just save it. I will tell you why I'm doing it. You will understand very shortly. And just close this file. Now what you do is you select your Verilog file of the 6-bit counter, right click on it and click on add module to block design. Now you can see our RTL description for a 6-bit counter has been added in the form of a block, where this block has 3 inputs, that is clock, reset, enable, and 1 output called count. Just you are visualizing our hardware module in the form of a black box with the input and output port list, and in the middle you can see the logo, that is RTL. So this block has been generated directly from your RTL code that you have written and saved in your design sources folder. If it is an existing IP, intellectual property, then you won't find this RTL symbol in that IP. So what do you mean by IP means? Just a quick understanding. So for designing a hardware, I told we need to write a description in HDL language. The HDL language is Verilog or VHDL or the system Verilog. So this is just a piece of a code. So if I want to share this design to any other people, so those people, if I give this code, they will easily understand and they will manipulate this code. But I want to share this design. At the same time, I don't want my code to be visible to them. So in that case, what I do is I will just transform this in the form of an intellectual property core, that is IP core. So how to transform this into an IP core, that we will see maybe by today afternoon or else in tomorrow's session, how to design a user defined IP. So in that case, what it will be doing is you will be able to generate an IP block similar to like this, but you will not be able to see the underlying RTL code. Only you will be able to see this block, and you that end user can use this block in their designs. So say for example, for all the logic gates you design an IP, and then if you double click on the IP, you will get an IP customization menu like this. So since this is an RTL code, we have not written any customization, so there are no options over here for us to edit. Maybe you can give some privileges to customize your IP, so that whatever the customization options are available, he will be just editing those options and clicking on OK. And then the IP will be configured with those predefined settings or user defined settings. And at the time of synthesis and implementation, what it will do, by using the underlying RTL code, it will try to implement a circuit. But still the user will not be able to see the RTL code. Only he will be seeing at the top level, it is in the form of a block with inputs and outputs. Along with this block, you will be providing some reference manual. So like how to use this block, how to connect, what are the significance of these inputs and outputs, that you will write in a one small PDF that we call it as a data sheet or a reference module. So what is clock, what is reset, what is enable, what is count, like that inputs definitions and output definitions you will write on a piece of a document, and you will share this block to any end user, so that he will just use this block, but he won't be able to edit or access your RTL description or Verilog code underneath it. So that we call it as an intellectual property core. The uses of intellectual property core is like we can reuse these cores in our existing design, in our designs, so that you need not always depend on writing your own HDL codes for each and every design. For generic blocks, maybe like a counter, shift register, for a clock signal generator, so on and so forth. These are commonly used in most of the designs. So if you have an existing IP, in industrial standard, what the people will do is, to the maximum extent, they will use the IP cores. Why? Because these IP cores are already designed and fully tested. So again, people will not waste their time in designing the basic building blocks. So if they want a counter, they won't again redesign the counter by writing Verilog HDL code. Instead, if an existing IP is available that is fully tested and authenticated, they will go directly to the existing IP. They will take that IP, they will put into their design, and they will reuse it. So mainly they will work or by writing RTL description to their own desired functionality for which IP is not existing. For the rest of the cases, they will try to reuse the existing IPs in their design in order to minimize the total design time and also to meet the time to market. Why? Because the VLSI industry is completely like a, you need to get into the market as early as possible. You cannot sit for a long time in designing your products. So you need to design your product as early as possible in order to reach a less time to the market. So this is a brief overview of what is an IP. So we will look into the IP in the subsequent sessions. So this also seems to be looking in the form of an IP, but this is not actual IP. Why? Because this is the RTL code converted into a block design. So it's kind of an IP block, but you can still able to see the RTL code over here, right? So this is not actual IP. That's why you have written, it is written as RTL. A logo is placed on this box. Now what we do is we try to interface few IPs for this counter design. So first we talk about the clock. Earlier what we did is we connected this clock input to the onboard crystal oscillator clock on the FPGA development board that works with default clock frequency of 100 megahertz. But there if you directly connect to the onboard clock pin, but you won't have any controllability on clock frequency. So whatever the onboard clock available and what is the default frequency it is generating with which it is operating, so you will be deriving the same clock with that same clock frequency in order to operate your module. But in the high-end designs, you need to customize the clock frequency. You need one device to operate at a clock frequency, say FC1, and another device with respect to a clock frequency FC2, where FC1 may be less than FC2 or FC1 is greater than FC2. So in industry standard, we will be using not a fixed clock. We will be using a clock with a variable frequency. So again, in order to generate a clock signal in digitally in the digital circuits, what we do is we use a clock frequency synthesizer. So for the clock frequency synthesizer basically works by taking a reference clock, and if you want to if you want the operating frequency which is lower than a reference clock frequency, then you have to do clock divider. So you need to divide that clock in order to get a reduced clock frequency. Say for example, if you want an operating clock frequency that is greater than the reference clock, then you need to do a clock frequency multiplier. So there are few design techniques like how to do design a clock frequency divider or a multiplier, so on and so forth in the literature. Even you can write your own custom Verilog HDL codes in order to generate a clock signal, but we don't really waste our time in writing the custom hardware description, maybe in Verilog or VHDL, for a clock frequency synthesizer. Why? Because in Xilinx Vivado, by default we have an intellectual property IP core in order to generate a clock signal with a desired operating frequency. So now what I do is I will add that IP core from the existing IP repository of provided by the Xilinx Vivado. So how to do that? So on top screen you can see there is a plus symbol that indicates like add IP. So if you click on that, you will get one menu. You can search this menu, or else in the search box you can type the IP name that you are looking for. And the IP, default IP in Xilinx Vivado, in order to generate a clock signal with the desired clock frequency, the IP name is called Clocking Wizard. So I will just type the name Clocking Wizard. CLOCKING. So once you type the name, it will filter out the menu and it will give you the desired IP that you are searching for. So now we have a clocking wizard. So you double click on the clocking wizard. Now it is telling like adding the IP. So if you want to refresh the layout, you can click on this anti-clockwise circle diagram, regenerate layout. So it will rearrange the position of the blocks. You can just click on control and scroll to have a. So here you can see this is a IP block. So it is plain, right? There is no RTL logo on this block. This means like this is a pure IP block. So what type of an IP? This is an inbuilt IP. Who is providing this IP? Xilinx is providing the IP. Even if a user also can make user defined IP that also looks similarly more or like this, but it will be a user defined. We will see how to design our own IPs in a later part of the FTP. Now for this IP there is also a RTL code associated with this, but we don't have access to the RTL code. Why? Because it is fully encrypted. Only at the top level we can alter the parameters. Accordingly, the RTL code will be customized automatically, that we cannot see it. Why? Because it is licensed under Xilinx. When you do synthesis and implementation, at the background, the RTL will be handled by the Vivado, and by using the RTL code of this clocking wizard, the clock frequency synthesizer will be configured, and corresponding bitstream file associated with the clocking wizard will be generated along with the bitstream components with respect to the entire design. So now we need to customize this IP. So to customize this IP, what we do is we have to double click on it. Now we will be getting an IP customization window. So on the left hand side, you can see IP symbol. It has so many number of input ports and output ports. Most of them are disabled. And you can also see the disabled ports. Why? Because on the left hand side, on the topmost corner, it has a checkbox is there, show disabled ports, that is selected. That's why we can see what are the total number of inputs and outputs this IP core is offering. So this has so many inputs and output ports with respect to the interface logic. So there are so many type of interfaces like AXI interface and native interface. Let's not go much into much details what is AXI and all. So for time being, I will remove this checkbox. You can see only few inputs are there: clock in 1, reset, and 2 outputs, locked and clock underscore out 1. So by default, what this is a native interface. AXI interface in the sense it has the inputs and outputs has one protocol, that is AXI protocol. With respect to the protocol, there are so many inputs and outputs. So in our design, we are not using any AXI interfaces. So AXI, we call it as AXI. So let's forget about it. We are only relying on our user defined inputs, that is general purpose inputs and outputs. So that is we call it as native interface. So that don't have any standard protocol and all. So This input has a clock in one and a reset. This you have to give to this IP. So this reference clock is nothing but our onboard clock signal that works at 100 megahertz. The output clock out one can be of any desired frequency that you will be customizing it. So in the clocking options, I just leave them as default. So don't change any options. In the second menu, there is an output clocks available. So click on that. So I think you can generate up to 7 different clock signals by using a single IP. But we are only interested in one clock signal. If you want 2 clock signals, you can check clock underscore out to. And on the left hand side, you can see IP diagram has been updated with 2 output clock signals. But for us, only one clock signal is sufficient. So I will select only one clock. And here you see what is the requested clock frequency. So you can give any desired frequency. Maybe I will use some 50 megahertz. You can use any other frequency of your choice. You can use either a reduced frequency or an increased frequency with respect to 100 megahertz. And the duty cycle of the clock by default is 50%. So I'm not changing that. And the remaining options, I'm leaving it as a default. And I'm clicking on OK. And you can see what is the reset type of this module. It is just like active high. If you want active low reset, you can click active low. Once you click on active low, you can see for the reset input, a bubble is added at the input that is indicating like active low. So I will keep it by default active high and I will click on OK. Now my clocking wizard has been customized to generate a clock signal with a frequency of 50 megahertz. That is an output clock that is named as clock underscore out one. With reference to the input clock that is connected to the clock underscore in one that operates at 100 megahertz, and this clock signal is coming from an external onboard clock pin on the basis strip board. So this clock one, I need to connect it to the onboard clock pin. So to connect that, I want to make this clock pin as external. So select that pin and click on make external. So now we got an external pin. This pin we will be connecting to the onboard FPGA clock pin. Now what I suggest you is, I suggest you people to select the clock pin. Once the clock pin is selected, and on the left hand side you can see external port properties. In the external port properties, you will be having a net. The name of the net as clock underscore in one underscore 0. I suggest you people to rename it as clock and press enter. So it is renamed as clock. Next, the reset input of the clocking wizard IP core. I just want to provide this reset signal directly from the FPGA board. So on the FPGA board, there are some push buttons. So the basis tree FPGA board. So what I will do is I will configure any one of the push button on the FPGA board to give reset signal for the clocking wizard. So for that purpose, again, I will select that pin and I will make it as external. Why I'm making this external? Because I want to provide these inputs from externally to the FPGA. So these are present outside the FPGA on the FPGA development board. So that's why I'm making them as external. Again, you select this reset and go to external port properties, and there you just rename it as just a reset, not reset underscore 0. So the renaming is successful. Now what I do is this clock underscore out one output of a clocking wizard IP core. So this is a derived clock, right? Which is having an operating clock frequency of our desired frequency that we have set, that is around 50 megahertz. this derived clock, I am going to connect it to the clock input of our counter module. So to do so, just click on the clock underscore out one pin. You will get a pencil kind of an icon and drag it and connect it to the clock input of our hardware module. And again, you can click on this regenerate layout. It will rearrange to the proper format. Zoom in. Now I told you like this clocking wizard will be able to generate any clock signal with the desired clock frequency. So how it is able to generate means inside it on FPGA it will try to use a PLL, that is a phased lock loop. So it is just a programmable clock frequency synthesizer. So once you have given your desired clock operating frequency, the PLL will be configured to generate a desired clock signal with a desired clock frequency. So I think you might be aware of the PLL mechanism. It has a locking phase. I just don't want to go in deep details of the PLL. You can just have a quick reference later on. So immediately when you switch on the circuit, you won't get the clock signal immediately or at least at a particular instant. Why? Because the PLL goes into a locking mechanism phase in order to perfectly establish the clock signal with the desired frequency. Once the clock signal has been established after the locking mechanism, at that time you will be getting the actual clock signal. So whenever the PLL is locked, the locked output will be active high. So whenever the PLL is in the it is not properly locked, that means the clock signal is not stable. When the clock signal is stable and it is generating with the desired operating clock frequency, then the PLL locked output will be active high. So what I'm doing is when the clock is not stable, the locked output is active low. At that time, when the clock is not stable, I am using that active low signal to reset my counter module. Once the PLL is locked, then it indicates that my clock is stable. When the clock is stable, then only I need to operate my counter module. When clock is not stable, I should not operate it. So during the unstable phase of the clock, the locked output is active low. For that entire duration, I want to reset my module. That's why I connected locked output to reset. When the clock becomes stable, then I will be reusing my module. At the time, reset should be disabled. So when the clock is stable, locked output will be active high. So this locked output only I want to use it as a reset. So our module should work when the clock is stable. So clock is stable means locked output should be active high, right? That is the reason if you give a active high reset, then your module will be reset for all the time continuously. That is the reason I used our module reset to be active low. Why? Because in the clocking wizard, the locked output will be active low for a small fraction of time, and once the PLL is locked, forever the locked output will be always active high. That is the reason what I did is I made our module reset to be active low. Why? Because I just wanted to reuse the locked output as the reset signal for our module. Otherwise, what we have to do if our module is still having an active high reset means we need to use a inverter in between locked and reset. So in order to avoid that extra logic, in order to directly connect the locked output of the clocking wizard IP core as a reset signal to our counter module, what I have done, I changed the reset from active high to active low. This is the reason that I told like I will be explaining later on. Next, what I'm doing is this enable input is there and count output is there. These I have to connect. So this enable input, if you want to connect to a slide switch, again you can make it external. Once you make it external, this pin you can connect to a onboard DIP, that is slide switch, to make it through which you can view this input. Already we are familiar like how to use how to connect these slide switches to the inputs and to the inputs of our module. So let us in this time not use this slide switch. What I will do is I will use an IP core. So for that purpose, what I do is there is an IP core that is called as virtual input and output, that is VIO. So you just search a VIO in the IP catalog. So you'll get a virtual input output, that is VIO. You double click on it. So now what is this virtual input and output? So I will just explain quickly. So you have your module over here. This is your counter module. This has some inputs. This has some outputs. Maybe counter or any other module. Not only counter, any other module. Now you have VIO. This is virtual input output IP core. This also has some inputs and outputs. So as the name suggests, virtual. So inputs and outputs. The inputs and outputs are virtual. Physically they are not existing. They are existing only in virtual concept. So as the name indicates, virtual inputs and outputs. So this is a VIO. It is providing virtual inputs. So this is a module, any module. This is providing some inputs to our module virtually. Not physically, virtually. It is providing inputs. So this is a module, right? To this module we have inputs. These inputs, instead of connecting to slide switches physically present on the FPGA development board, we are using a VIO to provide these inputs virtually. So how these inputs are coming? Module, and the outputs of the module are connected to the virtual inputs of the VIO. So this bypasses the physical connections or mandatory connections that you will be doing via the onboard slide switches or the LEDs. So this is the concept. So now if you observe here, we in our module that is counter 6-bit, we have an input called enable. Now we give this enable virtually via a VIO output. So for that, from the VIO, from the output, you have to drive the input of the enable of the counter. So what we have doing is you have to customize this VIO. So it is asking, when you double click on the VIO, it is asking how many number of input probes and output probes that you require. So I don't want to observe this output of the counter in VIO. That's why the input probes are making it 0. I only want to provide input to our counter module. That's why I'm only choosing one output probe for the VIO. And the width of the output probe is 1 bit. Why? Because enable is also 1 bit. If it is a bus, I will give more than a value 1. So click on OK. I customized this VIO IP core and I totally removed the inputs to the VIO. So it is only having one output, virtual output. This output is going to drive the enable input of my counter. So to this VIO, first we need to provide clock signal. So what I do is I connect the derived clock signal to the VIO and a probe underscore out 0. This output of VIO I connected to the enable input. Now I just rearrange. So this is how it looks like. So by using a virtual input output IP core, we are driving the enable input of our counter. Next, finally we have our count output. We want to visualize this output. So for that purpose, what I'm doing is I am adding another IP core, that is ILA IP core. ILA. ILA stands for Integrated Logic Analyzer. If you double click on that, you will get ILA IP core. And one more thing about VIO IP core. So you have a module, right? It is giving an output. This output I told like you can connect to a VIO to check it in the VIO interface. You can connect to the virtual input of VIO. But if this output is a constant output which does not varies with time, means it is just a scalar output. So initially it is something 0. After performing some operation, you will get some value that is fixed. Those kind of outputs you can just observe in VIO. But with respect to time or with respect to a clock signal, if the output is varying continuously, then you cannot observe it in VIO. You will observe only the end value, but not the intermediate value. You will be only able to observe when the simulation is ended. You will only able to observe the end value, but the previous values you won't be able to observe in the VIO. So that is the drawback. That's why what I did, I'm not connecting this count output to the VIO input probe. That's why I removed the entire inputs. I am only configuring the VIO output to provide the enable input to the counter, because enable is like a constant output. So for a fixed time, I'm making the enable to be 1, or else I will make enable to be 0. So during this interval, we will get a count output. This output I need to observe, right? Again, if I connect it to VIO input, the output is continuously changes that we cannot see. That is the reason I am not connecting to VIO. Instead, I am using another IP core that is called as ILA IP core. That is Integrated Logic Analyzer. So again, for this, what I do is I need to customize it. I will double click. By default, the interface type is AXI interface, but I'm just changing that interface to native. Why? Because we are not using any AXI protocol. And number of probes, I'm selecting it to be 1. Why? Because I'm only interested to capture one output. And now what I'm doing is under the probes, I have to select what is the width of the probe. So if you see here, our count value is of count output value of our counter is 6-bit. That is 5 down to 0. It is 6-bit. So we need a bus with a 6-bit line. So the width of the bus should be 6. And without disturbing the other options, I'm leaving it to default. I'll click on OK. Now our integrated our integrated logic analyzer IP core is customized. Now I'll just rearrange. Now what I do is first I'll connect the clock pin to the derived clock signal. I'll rearrange. Next, count output of our counter that I connected to the probe 0. I will rearrange once again. So with this, my all interconnections are been completed. And now what I am doing is I'm just saving my design. Click on save. Now design is saved. Only thing you need to make sure whenever you are making connections between one module to another module, the data width or bus widths should match. Here count is having 5 down to 0, and the probe that I used also has a width where that is 5 down to 0. That is total 6 bits. So with this, the block design has been completed. Now what we have to do, whether all the connections which we have made, whether they are valid or not, or else we have missed any connections that we need to make confirmation. For that, you can see here on top, there is a tick button that is a validate design. So you please click on that. It will run a validation check, and after the check, it will give you a display that validation whether it is successful or not, and there are no errors or critical warnings in this design. If for suppose if you forgot to connect any port, then it will show that validation is failed, and it will show you a message like you have not made some necessary connection. So I think we have completed the block design. Now the further step is to transform this block design into RTL netlist, after that synthesize netlist, next implementation, next bitstream generation, and then put it on FPGA. Shall we continue, or else we will meet after lunch? So sir, please confirm. Now the time is 12 o'clock, right?
Sir. Hello, sir.
Sir.
We will continue after lunch, sir.
Sir?
We will continue after the lunch at 2 o'clock.
We will continue after lunch at 2 o'clock. So we will take a break from here?
Yes.
Okay, then dear participants, we will take a break over here, and we shall continue this session after lunch. I hope all the participants has completed the design flow up till here. If you have not completed, or if you are lagging behind, try to complete the design step up till here, so that we will be able to continue our design subsequently. Why? Because the subsequent process is a tedious process. It will be very time consuming. Again, if you are not finished over here, it will be very difficult for you to follow my instructions. So Mahesh sir, please check that the participants at your conference room, everyone complete up to this step. If they are facing any difficulty, you please assist them.
I will, sir.
Okay then, I am closing from my side, and we will meet at 2 o'clock, and we will continue this session. Yeah, thank you.